talking about. So first of all, what is a lattice point? So a lattice point is basically just a point in the Cartesian system such that both x and y are integer values. So for example, like 4,5 or 6,7, like anything where both x and y are integers. And as long as they're both integers, then you have a lattice point, right? So like for example, 4.5, 7.5, that's not a lattice point because they're not integers. There's also things called like a point lattice, which is basically where you just have a regular spaced array of points, which can be different shapes. So like arranged in different shapes, like a square, rectangle, hexagon, things like that. But the most common way you'll see it is just Cartesian coordinate system, which is just, like a square. So if not specified, if not otherwise specified, it'll always just be a square. So here's an example. So on the left is just a square, like coordinate system, square. So all of those points that are marked there are lattice points. And you know this because, let me annotate. And you know that these are lattice points because a lattice point is basically just where the lines intersect, right? Because they have to be integer values. So for example, in each of, well, that was a really bad line, but in each of this, like this, in these two lines, this point is where it intersects. So that's a lattice point. So any point where two lines intersect and are integer values is a lattice point. And then the grid on the right shows a point lattice that is like, I think this one is a hexagonal one, but again, it's the same idea because you have different lines. And as long as these lines intersect in a spot, then you have lattice point. So like this is a lattice point, this is a lattice point, this is not a lattice point because the lines, like it's not intersecting, like there isn't a point there, right? But typically you won't ever see point lattices other than the one on the left, which is just a normal square. So you'll typically always encounter it in this form. So let's do an example problem. So this is kind of like a warm-up. It's pretty easy. So I'll give everyone like a minute and you can just send me the answer once you get it and I'll go over it.
谁讲谁不讲？嗯，谁主讲？
Okay, I'll go ahead and go over this. So it says a point lattice is constructed by plotting all the points a comma b such that a and b are positive integers. How many points in the point lattice lie on the line y equals negative 3x plus 8? So it goes over the point lattice that we talked about, which is basically just, like I said, the grid of points, right? A grid of points with integer values. So we need to find how many points in the lattice lie on this line, right? So if we have, I mean, we can sketch it out. It always helps when you have like coordinate problems to sketch it out. So if we sketch it out, we can see, oh, let me draw. So we have y equals negative 3x plus 8. So it'll look something like this, right? Obviously, it's not to scale, but it'll be a negative slope with a y-intercept of 8. So the line will look like that. But we need to find how many points that are integers actually lie on this line. So we can, I mean, because these numbers are pretty small, we can test them out. So a and b have to be positive. So we can start with a equals 1 or x equals 1, right? So if x equals 1, we plug it into the equation, and we get y equals negative 3 plus 8. So y is equal to 5. Okay, now let's try the next one. So x equals 2. So x equals 2, then we plug it in. Y is equal to negative 6 plus 8, so y equals 2. And then for x equals 3, y is equal to negative 9 plus 8, which is negative 1. And here we get that y is a negative integer. It's negative 1. And in the problem, it says that a and b are both positive. So y equals 1 is not a solution. So we only have 2 points, 1, 5 and 2, 2. But if these numbers are really big, then we obviously wouldn't be able to test everything out. So another way you could do this problem is, because they have to be positive, just go ahead and set negative 3x plus 8, which is y, right, to be greater than 0 because it has to be positive. Then you have negative 3x is greater than negative 8. And so x will be less than 8 thirds. and 8/3 is around like 2 point something. This is really bad. It's about like 2 point something, so x will have to be less than 2 point something. So x can only be 1 and 2. So in this case, you could just test them, but if the numbers got really big, you would have to set y to be greater than 0 and then solve for what values x could be. And then that way you could figure out how many values x could be for y to be positive as well. So in this case, there's just 2, so it wasn't that bad. Okay, so let's go over Pick's theorem. So Pick's theorem isn't something that you'll see super commonly in AMC, but definitely there are applications of it, and also in other like competitive math. There's definitely like Pick's theorem has come up multiple times. So Pick's theorem basically just expresses the area of a polygon whose vertices are lattice points. So if it gives you a shape with like a bunch of lattice points on it, and it tells you to find the area, instead of trying to like count the squares or count the triangles to find area, you can use this formula. The formula is A is equal to 1 plus 1/2 B minus I. And A is the area, I is the number of lattice points in the interior, and B is the number of lattice points on the boundary. This way you can just plug it into the formula and you can find it super quick. Let me show you an example of this. So for example, let's try to find the area of this polygon using Pick's theorem, right? So if we go back and look at this formula, it's I plus 1/2 B minus 1, right? So let me go ahead and write this formula here so you can see it. So area is equal to interior points plus 1/2 of the boundary points minus 1. So like if this were like 6th grade me and I didn't know Pick's theorem, I would have to start counting. Like there's this 1 square, this is 2 squares, 3 squares, and then you have to count the triangles. And like how would you count this, for example? This little triangle. So you can use Pick's theorem to find the area of this polygon. So what we can do is find the area is equal to how many points are in the interior. Well, we have 1, 2, 3, 4, 5, 6, right? 6 plus 1/2. How many points are on the boundary? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it would be 1/2 times 11, and then we go back to minus 1. So area is equal to 6 plus 1/2 of 11 is 5.5 minus 1. So area is equal to 11.5 minus 1, which is 10.5. So this is a lot easier than trying to count all the squares and triangles and the segments of triangles. You just plug into the formula. So let me clear all this. And then I'll give you guys a practice problem. So I'll give you like a minute to work on this one. Just find the area of the polygon using Pick's theorem. Okay, I've gotten a couple answers already, so I'll go ahead and go over it. So again, it's really simple using Pick's theorem, right? So area is equal to the number of points in the interior of the shape plus half the number that's on the boundary minus 1. And there's like a proof for this for Pick's theorem, but I'm not going to go over it. You can always Google it if you're interested, but I'm just going to tell you what the formula is. So in this case, let's see how many points we have in the interior. We have just 3, right? So 3. And then we count on the boundary. So there's 4 points here, another 4 here. That makes 8. And then we have 9, 10, 11, 12, 13 points on the boundary, right? So our area is equal to 3 plus 1/2 of 13 is 6.5 minus 1. So our area will be 9.5 minus 1, which is 8.5. So again, it's just an easier way of finding the area of a polygon without counting, how many triangles or whatever. Okay, so let's go over a lattice point problem. And of course, lattice points specifically won't come up, like they won't explicitly tell you things like lattice points, but it helps you with coordinate geometry problems. So this is an example 1. So it tells you, this is the AMC 12A problem 12. So I'll let you guys like try to figure this out for a minute or two, and then I'll go over it. So let's try to work on this problem. Okay, it's been a minute or two, so I'll go ahead and go over it. So it says that a line passes through point A, which is 1, 1, and point B, which is 100, 1,000. How many other points with integer coordinates are on the line and strictly between A and B? So when it tells you integer coordinates, you should automatically think of lattice points, right? So you can't have decimals. And again, it says, so we should point out the key features of this problem. So it says strictly between A and B. So we can't include 1, 1, and 100, 1,000. So because we need to figure out that the line passes through it, we need to figure out, first of all, I would figure out the equation of the line, or at least the slope, right? So given these 2 points, A, 1, 1, and 100, 1,000, let's go ahead and find the slope. So the slope will be equal to y2 minus 1 over 1 over x2 minus x1, right? Which is 1,000 minus 1 over 100 minus 1, which is 999 over 99. Divide top numerator and denominator by 9. And you can't simplify this further. So it's just 111 over 100 is your slope. And now if we plug it in to find B, I mean, you could. Wait, I mean, we can do it really fast. So 111. Sorry, my mouse glitching. And we can plug in the point like 1, 1, right, to find B. So then B will be equal to like negative 110 over 11. So, but the thing is, like, these numbers are kind of like not that fun, right? Because you have denominators of 11, and then trying to figure out when y is an integer for 111x over 11 minus 110 over 11. Like that's like really, it's pretty difficult to do, and you have to use like mod and stuff, and it's like mod 11. So I would like not recommend trying to find integers of this equation. So I would do instead is, let me just go ahead and clear all of this. So what I would do instead is when you have the 2 points, 1, 1, and 100, 1,000, what you can do to make it a little bit easier is transform the line. So a line that looks like, a line that looks like this. So it was like, slope was like something like this, right? No, wait, B was negative. Something like this, right? So if we transform it and we move it up a little bit, it won't change the problem. So let's just move it so that the 1, 1 is actually on oh, that drawing's not accurate, but basically you get the point, right? So we're just going to transform the line so that the point A 1, 1 is actually now 0, 0. So we're going to subtract 1 from all of the coordinates and transform the line, and it won't change the actual problem. So let's transform the line. So A 1, 1 will actually become 0, 0. So we're going to just move it. And then because we moved A down 1 and left 1, we're going to have to do the same thing with B. So subtract 1, which will get 999, 999. Right, and this way we just won't have a like weird B value. So our slope is still the same because we didn't transform the slope of the line. We just transformed the position. So our slope is still 999 over 99. It's still 111 over 11. It's just now that we don't have a b value, it's a lot easier to find integer values of y. So our equation is just now, right, and our y-intercept is 0 because our a is just at the origin. So now it's a lot easier to find integer values of y. So to make y an integer, x has to be a multiple of 11, right? So x can equal 11, 22, 33, so on and so forth. And the highest one we can get up to is 99, right? Because then after we get past that, it'll be way too big. So if we plug in 99, though, we'll get 999. And again, it says strictly between A and B. So we can't have 99 because that'll give us point B. So we exclude that, and so we have 11 all the way up to 88, which is 8 values, so our answer is D. In this case, it was just important for this problem to transform the line. So you can do that with these kinds of problems as long as you're not changing like the slope and things like that, and like the starting and ending points. As long as you're just moving the line, it keeps everything else the same. So it's a lot easier to work with. Okay, I'm gonna go ahead and clear this. So here's another example problem. So this one was pretty recent, it's from 2020. So again, I'll give you all like 2 or 3 minutes to work on this and then I'll go over it. Kind of long, but once you figure out what it's asking for, it's not that bad. Okay, I'll go ahead and go over this problem. So it says Andy the ant lives on a coordinate plane and is currently at the point -20, 20 facing east. So in this case, that is in the positive x direction. Andy then moves 1 unit and then turns 90 degrees left. From there, Andy moves 2 units, which is north, and then turns 90 degrees left again. He then moves 3 units west and again turns 90 degrees left. And then Andy just continues his progress, increasing his distance each time by 1 unit and always turning left. What is the location of the point at which Andy makes the 20th turn? So basically what it's saying is he's just turning in a spiral, and it's asking you the point at which he makes the 20th turn, right? Let's draw a diagram, because with coordinate geometry, it always helps to draw at least like some kind of sketch, right? So we have the coordinate plane, and he's currently at -20, or let me give myself a little bit more space. I'll draw it like over here. So at the point negative 20, comma 20, he'll be somewhere like over here, right? So like approximately. So he's facing east, so in the positive x direction. So and he first moves 1 unit. So like he's going this way first, right? And then he moves to so here, let's first draw the x and y. So the first thing he does is go 1 unit in the positive x direction, right? So we're gonna put a 1 here. And then he turns left and goes 90 degrees. So then he'll be going north. He turns left, right? And in this case, he goes 2 degrees or 2 units up. So we'll put that in the y direction because now he's going up. And then he turns 90 degrees left again and moves 3 units west. So when he turns 3 degrees, he'll go like this way, right? So he'll move 3 degrees in the negative direction. So we'll put a -3 here because now he's going in a negative direction, but it's still in the x direction. And then he goes down 4 units, right? Because he's turned left again. So it's like he's just going in a spiral basically. So he goes down 4 units, so -4 on the y direction. And then the next one he'll go is +5 in the x direction, +5 here. And then it just keeps going like that, right? So then next he goes like 6 up this way, and then 7 left, and then 8 down, so on and so forth until he does this 20 times, right? So we need to find a pattern for this because there's no way we're gonna, calculate where the position of each one of his turns is. So if you'll notice here, with every 2 turns in the x and y direction, he basically moves like in a negative, like in a -2 from his original spot. So we're just looking at the distance like displaced from his original spot. So in this case, for the y direction, it's the same thing. For every 2 turns, he ends up going like 2 degrees away from 2 units away from where he originally was. So we need to just figure out how many of these -2s we have. So because he makes 20 turns, 10 like half of those, so 1010 of them will be in the x direction, and then 1010 of them will be in the y direction. 1010 of them will be like on the left to right, and then 1010 will be up and down. So we have to divide those because every two turns gives us a -2. So if we divide those, we get 505, right? So we have 505 of these -2s. I realize you probably can't see this. Let me change the color. So every 500 and we'll have 505 of those -2s. So if we multiply that, we'll have a total of like -1010. So we basically divide it by 2 and then multiply it by 2. So in the x and y direction, he'll have displaced 1010 from his original spot, right? So let's look at the original x and y coordinates. So our original x coordinate was -20. And then we need to minus 1010 from that because that's how much he moved from his original spot. So we get -1030. And then in the y direction, he started off at +20. But again, he still displaced like 1010 from his original spot, which will give us -990. So the thing is like glitching. Anyways, so the x direction, this is x and this is in y. So your answer will be B. Sorry, I wrote all over the screen, but hopefully you can see that. So because we basically just need to figure out how much he displaced from his original position. And because for every 2 turns, he displaced a distance of -2, we just subtract that from his original position and we'll get our answer. So yeah, I should leave myself more space to write. I'll do that next time. So here's the next problem. So we have, this is another pretty recent from 2020 problem. So I'll give y'all like a couple minutes. Wait, what happened? Sorry, I don't know what happened. Anyways, here's the next problem. Oh, is it not working? Hold on. Let me leave and rejoin. Okay, sorry, I don't know what happened. Let me share my screen. Oh, I need to, yeah. Okay, there it is. Sorry. Okay, I'll go ahead and explain this. And if you don't know the answer, you can always just send me like what you're thinking or something like that. But so basically this problem is saying that a point is chosen at random within the square in the coordinate plane whose vertices are 0, 0, 20, 20, 20, 0, 20, 20, 20, 20, and 0, 20, 20. So basically it's just a square with those points. And then it's saying that the probability that the point is within d units of a lattice point is 1/2. So what is d to the nearest 10th? So again, the lattice points come into play. So before I kind of explain this problem, I want to go over locus because this problem kind of touches on locus. So the definition of locus, let me write it on the screen. So locus is basically just the set of all points that satisfy a given condition. And you can have locus in 2D and in 3D dimensions. So for example, if I have the locus of all points that are like d units away from this point, if we have like this is d units, and like this is d units, this is d units. There's like an infinite amount of lines that are d units away from that point, and it'll end up making a circle, this. So for example, one example of a locus would be the locus of all points that are d units away from one point is the circle with radius d, right? And there's all kinds of locus problems like that. And you'll probably, if you've taken geometry, then you'll know. But if you haven't taken geometry yet, then that's something that you'll learn in geometry. So for example, another one would be like, what is the set of all points that are like d units away from this line, like this infinite line? And so the locus of all points that are d distance away from this line would just be two lines that are parallel to this line that are d units away, right? So that's the locus of all points. So just things like that, where it's just basically a set of points that satisfy that condition. So in this problem, we're gonna end up using that. So let me erase all of this. Okay, so anyway, so we have a square, right? So let's go ahead and draw that. So we have a square. There we go. So we have a square, and it looks something like this, where this is 2020. Sorry. 2020, 2020. So we have a square like this, and we have a bunch of lattice points inside, like in like 2020 amount, right? But I'm not gonna draw all of them, obviously. So we have like a bunch of lattice points inside, and so let's just zoom in on one, because it doesn't really matter how many total ones we have. We could have like an infinite square, but we're only looking at the probability of one lattice point. So let's just zoom in a little bit and just talk about like 4 lattice points, right? So I'll just So let's zoom in on just like 4, for example. So if you have just 4 of these lattice points, we're looking at the probability that the point is within d units of it. So any lattice point that we draw in this giant grid of 2020 by 2020 will always be somewhere near these 4 points, right? It'll always be closest to these 4 points. You also, of course, you have other points like outside of it, but at that point, it's a distance of at least 1 unit away, and we only need a distance of 1/2. So we really only need to consider the 4 points that are around this specific lattice point. So what is the probability that it's within this? So again, we talked about the locus of any point that's within d units being a circle. So we can go ahead and draw the circle around each of these lattice points. So this is within d. As long as this distance is d, as long as the radius of this circle is d, anyways, as long as this radius is d, then as long as this lattice point falls within the circle, it would be within d units, right? And it's like that for all of these circles. As long as it's like the radius is d units, and as long as that blue point falls within that circle, it'll be within the probability, right? So, but of course, we're only looking at these four lattice points, so we don't need to consider the entire circle. So what we can do is just draw a quarter of a circle for each of them, because once you hit, like, for example, for this circle, once you hit this part, it's over a half distance away. So we really only need the quarter circle. So we can just draw like this part, this part, this part, and this part. So as long as the blue lattice points falls into any of these 4 quadrants, it'll be within the d units, right? So we need to find the area of these 4 quadrants. So the area of one quadrant is 1/4 pi r squared, right? Because it's a circle. Pi r squared. And we have 4 of them. So we can multiply this by 4. And this will, actually, it shouldn't be r, it should be d, because that's what it gives us. And then the 4's cancel. So we just have pi times d squared as our total units. And because it's a probability of 1/2, we have 1/2 times the unit of the entire square is just 1, right? So it's just 1/2. So we have that d squared is equal to 1/2 divided by pi, which is 1/2 pi, which is about like 1.62 something, 6.28 something. We'll just approximate it to about like 1/6. And if you have this memorized, 1/6 is about 0.16666, which is like 1.667. And because this is d squared, we can take the square root of this, and that's approximately 0.4, right? Because 0.4 squared is 0.16. So of course it's not exact, but it says nearest tenth. So our closest answer is B, 0.4. So in this case, you did have to use locus, but you just had to figure out like the area of those 4 quadrants and then use probability to find the find d to the nearest tenth. We'll go ahead and clear all of that. And we'll go to the next example. So this example also uses locus because it's the region consisting of all points in the space. So this last problem was in 2D, this one is in 3D. So you might have to kind of visualize it a little bit more, but I'll give you a couple minutes to think about that. And if you don't have an answer, just send me like what you're thinking, and that's okay too. Okay, so yeah, I've got a couple answers and like some thoughts and stuff, so I'll go ahead and go over this. So it says the region consisting of all points in three-dimensional space within 3 units of line segment AB has volume 216 pi, and then it asks you for the length of AB. So again, this has to do with locus because it's asking for the region consisting of all points that satisfy condition, right? And this time the condition is 3 units away from line segment AB. So we can kind of visualize this first. So remember when I said for the last problem that the locus of all points that are a certain units away from a line is just 2 parallel lines, right? So the same thing kind of, we have to break this into parts. The same thing kind of occurs here because it's a line segment in this case of AB. Oh, I have to keep forgetting to click draw. So we have line segment AB. So let's just pretend this is like A and B. Line segment AB. So first of all, because it's in three-dimensional space, we have to consider an extra dimension, right? So three units away will give us like a little, like I don't know how to visualize this, but basically we'll have like this is 3 units, and then this is like 3 units. So first we have these 2 line segments, but because it's three-dimensional, it'll go all the way around. So like if you have line AB, you also have like these lines. It's kind of hard to visualize. But you have like lines circling all the way around AB. Like if you have line AB, it'll go all the way around it. I don't know if y'all can see me, but the line AB, you'll have lines going all the way around as long as it's 3 units away. So it'll be kind of like a cylinder, right? Because it's every single line that's 3 units away in 3 dimensions. It's a cylinder. So you'll have something looking like this. So yeah, Brandon, you were on the right track. You have a cylinder, right? Cylinder, and then this is like A and B, right? Points A and B. So then everything around that cylinder, everything that's 3 units away from AB will be in that cylinder, right? But then we also have to think about, because this is 3D, and this is A and this is B, because we're in 3D, you also have to consider top and bottom, not just left and right. You have to consider the Y direction, A and B, and the Z direction, of course. But A and B, so there will be another like line segment. This is 3 units away. This point. We have another point here. This is 3 units away. This point is 3 units away. This point is 3 units away. This point is 3 units away. So it just keeps going like that. So there's an infinite amount of line segments that's 3 units away, and it's like above and below A and B. So we'll give 2 spheres also. Right here. So there'll be 2 spheres on top of A and B as well, because it's 3 dimensions, right? We have to consider the top and the bottom of the cylinder as well. So really it'll look something like this. This will be your image, right? We have the cylinder in the middle, and then we have the spheres on the 2 ends because it's, 3-dimensional. So let me go back to this. So let's go ahead and calculate the area of the things that we do know. I'll change the color. So we have the little cylinder. What's this? Like semi-hemispheres, I don't know. So first of all, the area of the two like half spheres is, the area of a sphere is 4/3 pi r cubed. And because we have, 2 half spheres make a whole sphere, so we don't need to half or double or anything like that. And we know that our radius will be 3 because we need everything to be 3 units away. So we'll get 4/3 pi times r cubed is 27, right? Which will give us 36 pi. So just the volume of these two like half spheres, hemispheres, will be 36 pi, but our total volume is 216 pi. Oh wait, that's the wrong slide. I'm so sorry. I didn't realize. Okay, I was on the wrong slide. So anyways, so we have 2 hemispheres and the total volume was 36 pi. And the total volume of the entire thing is 216 pi. So we need to subtract to find the volume of the cylinder, right? That's not a 3. So the volume of our cylinder will be 180 pi. And we know that the volume of a cylinder is pi r squared times the height. And we have that the radius is 3, so 9 pi times the height. And the height is the length of AB. So then our height is 20. And height, again, is the same thing as AB because in our cylinder, AB is our height, right? It's really sloppy, but AB is the height. So our height is D20. So yeah, that's how we will find the height. So in this case, it's the locus, and in 3 dimensionals, you just have to visualize a little bit better. So just know that not only do you consider like left, right, up, and down, you also have to consider in 3 dimensions, you have the Z plane. So you have to consider like the two spheres on the top and bottom. Yeah, and I think I'll end it there because I've been talking for